Hello, dear students. I am Samir Velankar. I welcome all of you to this next video on B tree. In the previous video, we saw what are the rules for creating B tree or how a B tree appears. And in this video, we are going to learn, or rather, in the previous video, we also saw what do you mean by order of B tree and how the distribution of keys are present and the rule of B tree we saw. In this video, which will be a major one, we will see how to construct a B tree of order 5. So order 5 means every node can have 5 pointers. Every node can point to maximum 5 children. That means every node will have capacity of 4 keys. But remember the rule, if the capacity of the node is 4 keys, then the node must store at least 2 keys. That is, we should fill the node at least half. But root node is an exception to this rule. Let's consider the data given below. The data is given in the sorted order. The keys given are 1 to 20. And these keys in this order are to be inserted in a B tree of order 5. So let's start with the construction. What we do initially is, because there are no nodes available right now in the B tree, we will be creating one new node, isn't it? Let us create a node, and the node we know is having order equal to 5. So definitely there are four places to store the keys because order is 5, and there will be 5 pointers. As order is 5, the number of pointers in the node are 5. Now what we do is we take the first 4 keys 1, 2, 3, 4 as given in the data, and we store them in the positions given. Now you note, we don't have to create any new node till now. If it was binary tree, then in a binary tree we would have created a node and stored 1 in it because the node has capacity of only 1 key. Then to store the next key 2, we will have to create a new node, isn't it? And then we will say this value 2 is larger than 1. So right pointer of 1 will point to this new node 2. But because in our B tree, every node has capacity of 4 keys, we are lucky and we don't have to create any new node so far. So good. But what happens really when we try to create or when we try to insert one more key, 5? The next key, let's take 5 now. The problem is this node, oh, by the way, sorry for this. By the way, this is the very first node created. So we will say root pointer. Root pointer points to this topmost node, isn't it? So whatever is the base address of this node, suppose the base address of this node is 1000, then root will store 1000 and it will continue to point to this node, the topmost node. All right. Now let's take 5, the next key, and try to store. But there is a problem. We cannot store 5 in this node because the node is full. Remember, the node has capacity to store only 4 keys as order is 5. So where should 5 go in that case? Now what a beginner might think here, and always it happens in the classroom also while teaching the students will appeal that, sir, why don't you create a new node? Logical thinking, obviously. I appreciate that because the above node, that is root node, is already full. So where will you store 5? You create a new node, but new node will also have capacity of 4 keys. Agreed? Every node has order 5, isn't it? So this new node will also have 5 pointers. 5 pointers. And you better store 5 here in the new node, they say. And then what about the relation of this new node with the existing node? Now we will say this new node becomes child node of the above node, and you see 5, the new value that we have added, is greater than 4. So the best pointer that can point over here is the right pointer of 4, isn't it? It can't go to the right of 3. 5 can't go to the right of 3, although 5 is greater than 3, but 5 should be less than 4. You know the distribution of keys from the earlier video. So the best place for adding this child, which stores 5, is to the right of 4. This is what students or any beginner will claim very early in the topic of B tree. But let me tell you one thing, that this B tree currently is wrong. Think over it. This tree is wrong. Why? Because the node which I am ticking right now, this node, new node, is not obeying the rule. It is not obeying the rule. What was the rule? The rule is that if 4 keys can be stored in any node, then at any point of time, at least half of that node must be full. At least half you should fill. What you have done is, capacity of this node is 4 keys, but you have stored only 1 key in this, and you have wasted 3 keys. What if you store one more key over here? Then it is valid because you are storing at least 2 keys. Half of the node is full. What if you store 3 keys? Oh, that's good. And what if you store all 4 keys? Then you have utilized the node to fullest of its capacity. But under utilizing the node like this is really bad. This is bad. And this disobeys the rule. I'm sure you are thinking about something. The same thing that students think in the class and even suggest. That they say, sir, you are saying that this node is invalid. Okay, I agreed this node is invalid because this is storing only 1 key and the rule is the node should be at least half filled. So it should store 2 keys, right? Then they say, sir, but there are many keys. Like 6 is going to join later. So 6 will be stored here to the right of 5. Then how will it be invalid? Hello, my dear students. You tell me, at the moment we have not stored 6. 6 has not yet appeared. At the moment we have stored only 5. So at the moment, isn't this node invalid, you tell me? At this moment, this node is not obeying the rule. By the way, what do you mean by rule? Oh, very silly question. What do you mean by rule? Rule is something which should be obeyed every time, isn't it? It's not like you can say, okay, I will not obey the rule now, but let's see, I will obey the rule later. What do you mean by that? Then it's no more a rule, isn't it? Or if you're still not agreed, that you are saying, no, no, sir, 6, 7, 8 will join later on in this node. So the node will become full. But you just imagine, what if 5 was the last key? Oh, now you might agree my point. What if 5, this much data was not given, only up to 5 was given. Then 1, 2, 3, 4 will go in the root node, topmost node. And then you will store 5 alone in one of the nodes. But the node has capacity of 4 keys and you are storing only 1 key, then it is invalid. This is surely invalid and it will remain a faulty node. I hope you agree. So this idea of creating a node for storing a new key like 5 is really ridiculous. You can't create a node like this. Let me erase this. Let me make it clean. Okay, good idea is I'll make the entire board clean and I'll redraw. What did we have? Just check this. Initially, we had 4 keys added in the root node. Oops, where is the cursor? Wait a minute. Yes. Okay. Initially, we had a node created which stores 4 keys. Very easily, we stored 1, 2, 3, 4 places. And it has 5 pointers. Now, these pointers, all of them will be initially null because there is no child, absolutely no child added to any of these pointers initially. All right. Now, if you are adding 5, the fifth key, we saw just a few minutes back that it is bad to create a new node which stores only 5. It will disobey the rule. So what do? You use a process called split and propagate. Very interesting. Propagate. Very interesting process. Okay, let's see what it is. 5 cannot be added in this node. This is full. But just imagine if you are allowed to add 5 in this node, where would you add it? Where will you add? Of course, you will add 5 after 4 because you know the entire node has to be sorted. Of course, phi doesn't have place in this node, but if phi was able to go in this node, it will go after 4. Now you see, we have got a sequence here. Sequence of keys 1, 2, 3, 4, 5. Okay, consider the new key in that sequence. Although valid values stored in the node are 1, 2, 3, 4, but assume phi for some time is in that node. But phi can't go in the new node, it is full. So you split this node into two equal parts. You split the node such that you create two new nodes from the existing node, such that both nodes will have two keys each. Two keys each. And the median of the sorted sequence, the median, that's 3. I hope you know what is median. Median is midpoint of the sorted sequence. Midpoint is 3 here. This median will be propagated up. It will be taken up. And this 3 will be stored in the root node. So we are going to get two new nodes. One node storing 1, 2, other node storing 4, 5. And 3, the median, will propagate up to become new root node. Let's see what we are talking about here. The node is split. We have got a new node now which stores only 3. Only 3. From where did this 3 arrive? This 3 arrived as a median and it was propagated up. This 3, the median, was propagated up. And 1, 2 became the left child and 4, 5 becomes the right child. So we have a node here, new node created, which stores 1, 2. And we have another node which was a result of split and it stores 4, 5. Now you all know every node has capacity of 4 keys, isn't it? So there are 2 keys vacant here. We have not utilized the 2 keys. I have shown underlined over there. And there are 2 keys vacant in this node also. We have not utilized these keys. There is nothing stored here. And the nodes at the bottom over here will again have 5 pointers. Each one of them will have 5 pointers. Isn't it so? So is the node storing 1 and 2 obeying the rule? Yes, it is obeying the rule. Capacity of the node was 4 keys and we have stored 2 keys. At least half of the node is full now. And is the node storing 4, 5 obeying the rule? Yes. The node had capacity of 4 keys and we have filled 2 keys. So we are filling the node at least half. Also observe, now to the left of 1, if you want, you can store some keys, isn't it? Because you know which keys to store to the left of 1. So you can have a child, left child of 1. You can have a child to the right of 1 and left of 2. You will know which keys to store here, isn't it? All keys greater than 1 but less than 2. And you can have a child node over here to the right of 2 because all values greater than 2 will be stored to the right of 2. So how many children, valid children, child nodes can be present for the node storing 1, 2? Exactly 3 children. That is exactly ceiling of 5 by 2. That is ceiling of 2.5. That is 3 children. I hope you are again visiting the rule of the B tree. Finally, the root node, you watch now, this is the root node which stores 3. Look how we have split the node containing 1, 2, 3, 4. 3 went up and it became the root. It joined the root in fact. And the 2 new nodes were created. Now obviously 3 has left pointer and 3 has right pointer. Every key has that. And the left pointer of 3 will point to the node storing 1, 2. Now observe, the key stored to the left of 3, keys stored to the left of 3 are less than 3, isn't it? And the keys stored to the right of 3, that is 4, 5, are greater than 3. Are you understanding it? Now, obviously, this node also has 3 more key capacities, isn't it? Yes, because capacity of the node is 4, but we have not utilized these keys at all. Not utilized. So the pointer over here will be null. The pointer over here, the next of this key also will be null. And this last pointer also will be null. So you can see root is not obeying the rule. Observe the root node. Root node is underutilized. Root node should at least be half filled according to the rule. But you might have seen the rule. Root node is exception to the rule. Root node can store less than half also. So if the capacity is 4, relax. Root can store even one key. That's allowed. But the other nodes must be at least half filled. Okay. Shall we continue? Let's see. Now let's take the next key. This is our latest tree, okay? The tree which I am ticking is the latest tree. Oops, where is the cursor again? Yeah, okay. Now this is the latest tree that we are having. Let's take the next key. You know the keys are sorted. So we just now added 5. Let's add 6 now. So where will you insert 6? Now remember, 6 will be always, or any new value will be always inserted in the leaf node first. So all these nodes which I am marking over here are leaf. See these bottom nodes, these are leaf nodes, isn't it? Because none of them are currently having any child. So if you are adding any new key, they should always, the key should must or key must go in the leaf node first. Okay, let's add 6. Start from root. Start checking from root. Where will you add 6? Of course, to the right of 3, because 6 is greater than 3. So you reach this node, and 6 can be added in this node where the mouse is hovering. Does it have place? Oh yes, it has place of 2 keys. So 6 can be stored in this node, and you know it's always sorted. So I will be storing 6 after 5. I hope you got it. Let's add the next key, 7. Remember, any new key must go in the leaf node first. So where will you add 7? Start checking from root. 7 must go to the right of 3 as it is larger than 3. So you reach this node, and 7 must be stored in the node which stores 4, 5, 6. And 7 has a place. One more key is vacant here. So you can easily store 7 in the node shown. But now the node is full, isn't it? Now what's the next key? Next key is 8. Well, 8 must go to the right of 3 because it is larger than 3. So it should go to the right of root. So 8 must go in this node 4, 5, 6, 7. But there is no place, isn't it? Node is full. So what do? You assume for some time that if 8 would have gone in this node, it would have gone after 7 because it should be sorted. So you get a sorted sequence here, isn't it? 4, 5, 6, 7, 8. And you divide that sequence, split that sequence into two new nodes such that 4, 5, the left sequence, and 7, 8, the right sequence, will result in two new nodes. And what about this median 6? 6 is the median which will be propagated up. 6 will be propagated up. Up means what? Up in the root. So you can see that 6 joins the root, 4, 5 becomes the left node, 7, 8 becomes the right node, and 6 gets propagated to the root. And root has enough room. Come on, root has 3 keys vacant, so it always welcomes 6, isn't it? So now what's going to be the latest tree? Let's see. We will now have in our latest tree the root node. Okay, what's root node going to now store? Root node is going to store 3 and 6. Note how this is also sorted. 3 followed by 6. 6 we got from one of the leaf nodes, and the key got propagated up to the root. Now what do you have at the bottom line here? We still have a node which stores 1, 2. Yes, everyone? Check the diagram above. 1, 2, and 2 keys are still vacant here. We have a new node now. What's that? 4, 5. This was the result of the split. And we have one more node which stores 7, 8 with 2 keys vacant here, 2 keys vacant here, and so on. Now understand the distribution of pointers. You see the left pointer of 3, this is the root node, by the way. Left pointer of 3 will point to the node which has the keys less than 3, isn't it? Now the right pointer of 3, that is left of 6, right of 3 is left of 6, will point to node 4, 5. Now you see this 4 and 5 are greater than 3 but less than 6. And the pointer to the right of 6 will point to the node storing 7, 8. 7, 8 are greater than 6. But still, you understand, that there are two keys still vacant in this. Two keys are vacant, and these pointers, these keys are not utilized, and these pointers will be null because there are no keys itself. So how can they point to any child? Also, all pointers over here, all pointers in this bottom nodes are null. So these are leaves. All these are leaf nodes, isn't it? So you understand all the pointers here are null. One thing you might have observed by now is that there are three leaf nodes now. Currently, there are three leaf nodes, isn't it, in this tree? And all leaf nodes are at same level. You observe the level. They are at same level. Root is at level 0, you can say. And all leaves are at level 1, isn't it? This is always true in the case of B tree, balanced tree. In a balanced tree, leaf nodes are always at same level. This is not always true with binary tree. In a binary tree, you may have a leaf here at this level. Then on the right side, you might have a leaf at this level, and you might have another leaf at one more level down. So leaf nodes can be at various levels in a binary tree. So binary tree may not be balanced. I am saying binary tree may not be balanced. May not be. It's not that it will be never balanced. You can have a binary tree in which luckily, all leaf nodes are at same level. So for instance, I may have a binary tree somewhat like this. If this is the binary tree, these are leaf nodes. You can see all the leaf nodes are at same level. Perfect. So this is balanced binary tree, but it's not compulsory that binary tree will be always balanced, isn't it? But what about B tree? In a B tree, you will always see that all leaf nodes are always at the same level. So therefore, B means balanced. I hope now you have understood. I was delaying this discussion of why B tree stands for balanced tree. All right then. I hope you are also understanding split and propagate process. Now let's take the next key. Next key is 9. We just now inserted 8, isn't it? So 9 will join where exactly? See the procedure? First check the root. 9 must go to the right of 6 because it is larger than 6. 9 can't go between 3 and 6. Come on, 9 can't join with 4 and 5. 9 is greater than 3 and greater than 6. So it should go to the right of 6. So 9 will join the node with 7, 8. There is enough room, so no problem with this. And 9 joins here. Similarly, the next key 10 joins here. Now 11 has got problem. The same process of split and propagate will continue. So 7 and 10 will be left split, 10, 11 will be right split, and 9 will be propagated up to the root. So you can understand that now the root node is going to store 3, 6, 9. The place which was vacant welcomes 9 now. And down under there, you will have two new nodes, 7, 8 and 10, 11. So let's see the latest tree, what we are going to have after inserting 11. After inserting 11, we are going to have a node, root node, which stores 3, 6, 9. Still one key is vacant in the root. Then we down there, we have got a node which still stores only two keys. 1 and 2, two keys are wasted again. We still have a node which stores 4, 5. What do you say? There's nothing changed here. But 7, 8, 9, 10, 11. This sequence was split into 7, 8 and 10, 11. I hope you understand 10, 11. Isn't it? Now the pointers left of 3 still pointing to 1, 2, less than 3. Right of 3 but less than 6 points to 4, 5. Right of 6 but, sorry, greater than 6 but less than 9. This pointer points to 7, 8. And larger than 9, that is 10, 11, is where this pointer points. Agreed? Now let's add more keys. By the way, you observe all these nodes which I am marking are leaf nodes, and all leaf nodes are still at same level. Emphasize on the point, this is a balanced tree, okay? Now let's come to the next key, 12. 12 will go to the right of 9. No need of explaining that. Start checking from root. 12 is greater than 9. It will go in this node, and this node has capacity of 2 more keys. So you can put 12 here. Then 13 will also join. So this node is full, but 14 the next key will result in the split. So 12, the median, 12, which is the median, will be sent to the root. 12 will be sent to root. So what will be the new root and the tree now? Let's see. The tree now will be the root node is now going to store 3, 6, 9, 12. I hope you are understanding we are heading to something really interesting. You will be thinking that after some time even root will be full. So how can you welcome a key which is propagated up? Let's see. Okay. We have got a node storing 1, 2, 2 keys vacant. Then we have got a node which stores 4, 5. Then a node which stores 7, 8. Two keys are still vacant here. Then a node which stores 10, 11. And remember 12 was sent up to the root. We have one more node which stores 13, 14. Two keys are vacant. Now the pointers, as you see, no need of explaining anymore. The pointer over here, 3 and 6 will point to 4, 5. 6 and 9 pointer will point to 7, 8. 7, 8. 9 and 12 pointer will point to 10, 11. And last pointer, right of 12 will point to 13, 14. All right, let's add more keys. Suppose we add 15 and 16 and 17 wants to join. So now the split will send 15, 15 to the root median. Sorry, but there is a problem. How can root store 15 now? This is root and root is also full. So we cannot store any new key in this root. But 15 must join, isn't it? 15 is propagated up. 15 must join. So you repeat the process of split and propagate on the root node. You can imagine 15 wants to join this node, but 15 can't join. Then 9 will be sent up. This is the median. 9 of this key will be sent up to become a new root. 3 and 6. 3 and 6 will become the left split, and 12 and 15 will become the right split. Very interesting, isn't it? So let's see. What is the tree that we are going to now get? Now the root is going to store 9. See how the root node was split and 9 went up to join a new root. But the left of 9 is going to point to a new node which stores only 3 and 6. Two keys are still vacant here. This was the result of left split of root, and right of 9 is going to point to another node which stores 12 and 15. Remember 15 we got from one of the leaf nodes. It propagated up. It was unable to join root, so root was split. So 15 joins in the right child of 9. Now further down there we are having left child of 3, isn't it? Left child of 3 still 1, 2. Observe the diagram up there. And the right of 3 but left of 6 is still pointing to 4, 5. There is no change over here. And the right of 6 is still pointing to 7, 8. Okay, and the other pointers over here will be null because the keys itself are not stored. So other two pointers will be null. Okay, what about left of 12? Well, the left of 12 will still point to 10, 11. Observe the next leaf in sequence over here, isn't it? So 10, 11 will become left of 12 because they are less than 12. Then what about 12's right and 15's left? It will point to 13, 14. Enough is enough, isn't it? I hope you got it. 13, 14 was the result of left split of the leaf, and the next pointer of 15 is going to point to 16, 17. Remarkable, isn't it? How many leaf nodes are we having now? We are having 6 leaf nodes, and all leaf nodes are at same level. You see, they are at same level. This is a balanced tree with 9, now only 9 stored in the root node. I hope you got the idea of split and propagate. Now, actually, we took the data as 1 to 20. Remember the question. But there is no sense in adding 18, 19. Now, you can understand if 18, 19 is added, they will be added in this rightmost node. Correct? And 20 can't join. So, this node is going to be split and 18 will be sent up. But 18 can be easily accommodated in the node I am marking. So 18 will be stored in the node which I have marked. That is 12, 15, 18 will be stored. sorry, and two new nodes 1617 and 1920 will be created over here. That's how we construct a B tree of order 5. I hope you have understood split and propagate. More about B tree is coming up in the next video. Thank you very much.